So this is going to be a lesson on 8.6 parallel circuits. So the do not question says, well, if we cut apart a series circuit, would electric current still flow? And if you think about it, in a series circuit, really the defining feature of a series circuit is that, well, there's only one pathway for electrons to go. That's really the defining feature of a series circuit. So if you kind of cut this part of the wire or one of these light bulbs stop working, well then the rest of the light bulbs in the series circuit also stop working as well because there's no path for electrons. Whereas in parallel circuits, there are multiple paths for electrons. So even if a light bulb burns out or you kind of cut part of that wire, well then the electrons can still go for the other paths, right? The electrons can still go for the other paths all the way around, but that light bulb just won't work. Right? So that's one of the advantages that parallel circuits have over series circuits. Parallel circuits have multiple paths, and that's really the defining feature. Parallel circuits have multiple pathways for electric current to flow through. Now let's talk about current in parallel circuits. Now, on your reference table, let me make this a little bit larger. And so on your reference table right here, where if you go to the parallel circuits part, you'll see that the current in a parallel circuit, the total current that runs through the circuit is equal to the individual current running for each resistor. So you'll see that the current kind of splits off into two paths, right? So my total current would be 2 amperes, but as the path split, you'll see that, well, my current also splits. Now it won't split 50-50. That's just, this GIF does tell you that it splits 50-50, but that's not always the case, right? It definitely depends on the resistor. So don't get misled by the GIF. The current does split and they all do add up to your total current, but they don't always split 50-50. So your total current is equal to I1 plus I2 plus I3, etc., right? As it says on your reference table. Now let's talk about resistance. Let's talk about this dam, right? So how do we increase, and I use this water analogy a lot. I'm sorry, I apologize. So this question says, well, how do we increase the water current here without changing the size of the opening? Right, so let's take, for example, this image. Let me screenshot this image right here. Let's make this a little bit larger. So again, we're not going to increase the opening, right? So the opening is going to stay the same, and there's still going to be the same amount of water on the top. So we're not changing the amount of water, we're not changing the size of the opening as well. Well, how do we increase the amount of water that's coming through? Well, one thing you can do is, well, you can kind of open more paths, right? So there are multiple paths here that you can also open, have water flow through. And when you open these paths, well, you increase the amount of water current. If you kind of relate this to voltage, right? If you kind of relate this uh, to parallel circuits, right? Circuits now. Well, if we wanted to increase my electric current, right? If someone wanted to increase my electric current, increase the amount of electrons that are flowing through a particular point in time, well, if each path gives me 2 electrons, and I'm not saying this is something you can assume for everything, but this is really just an analogy, but, well, now I can have a different path, and the more paths I open, the more electrons are going to go through. And so my electric current increases, right? So as I add more paths, my electric current increases. But due to Ohm's law, right? Due to Ohm's law, we know that R is equal to V over I. And if my voltage here is constant, and I'm trying to compare R and I here, right? If I'm trying to compare R and I, well, then I know that there's an inverse proportion here, right? So as my current goes up, my resistance, sorry, as my current goes up, my resistance goes down. So my equivalent resistance of the entire circuit goes down. Right? So my total current goes up, but my equivalent resistance goes down. And if you think about it logically, resistance is just how much am I impeding the flow of electrons? So if I have a faster flow of electrons, if I have more electrons flowing, well, then I have less resistance to that flow, right? It's just really the definition of the word. Feel free to pause this video if you need to kind of read this slide, right? And so also, if you take a look at the GIF, right, as you can see, more paths allows more electrons to flow, more current, but you'll have a smaller a smaller resistance, yeah. Oh yeah, and the formula for equivalent resistance is what you guys see here, right? So 1 over Req, that's a 1, not an I. 1 over Req is equal to 1 over R1 plus R2 plus 1 over R2 plus 1 over R3. Let's move on. Now, voltage in parallel circuits, and you'll see right here, right, your voltage is the same across all resistors. So it's really equal to the voltage of the battery. Right? So the voltage across each resistor is the voltage of the battery itself. And if you kind of think about it, really all these paths are connected. Doesn't matter if one path is shorter than the other. The difference in potential, right? There's a certain amount of electrons on the top. You kind of go back to this dam here. There's a certain amount of electrons on the top and a certain amount of electrons on the bottom. And well, there's still the potential difference. The difference in energies between the top and the bottom here really is the same. So you can kind of think of it that way, right? It doesn't matter how many paths there are. If they're all connected in parallel, the voltage across each path also drops, or rather is also the same. So the voltage across each resistor is the same in parallel circuits. That's really just something you need to remember. Again, when we're solving problems, when we're using Ohm's law, we really are either going to use my total resistance, right? So let me just erase all of this, erase all ink. So we're either getting my, let's go back. So we're either using my total resistance, right? So equivalent resistance equal to voltage. Voltage is the same across all resistors, so it doesn't matter. Is equal to the total current. Or if I'm solving for individual resistors, again, I'm going to use voltage there, but I'm going to use I1 instead. Again, I'm never going to mix or match. I'm never going to mix these kind of values. I'm not going to say total resistance, my equivalent resistance is equal to voltage over current 1, right? Current running through resistor 1. I have to use either my total or I have to use either my individual. One or the other. One or the other. So let's take a look at 6a. Let's take a look at 6a. So calculate the equivalent resistance between R1 and R2. So R1 is 15 ohms, right? So that's R1. R2 is 30 ohms. And then you have a voltage, right, of 60 volts. And you want to know, well, what is Req? Now, one way to solve, well, we know that on your reference table, the formula for Req is this, right? So it's 1 over R1 plus 1 over R2. So Req is equal to 1 over 15 plus 1 over 30. And so now, well, how do we solve this? Well, there are two ways to solve this, or multiple ways. One way we can solve this is, well, we can kind of use a common denominator, right? Because you'll see here that there's a common denominator here, and the common denominator is 30. Well, how do I get 1 over 15 with 30 on the bottom? We'll have to multiply this number by 2, right? So if I multiply 1 times 2 and 15 times 2, I get 30 on the bottom and 2 on the top. And well, now I can add them. Now I can add them. And now I get 3 over 30. And now a special thing you can do here is that, well, you can flip it. You can flip this fraction, right? So I can flip this Req on the bottom and make it go top. I can do the same thing for the other side. And so now I have Req is equal to 30 divided by 3, which gets me 10 ohms. So my equivalent resistance here is 10 ohms. And this is definitely one method of solving it. And I'll show you the other method now. So again, Req is equal to 1 over 15 plus 1 over 30. Now, let's say you don't know how to do a common denominator. Well, one thing you can do here is, well, you can just plug this into a calculator, right? You can do 1 divided by 15 plus 1 divided by 30. Right? And what you get is you get 0.1. Now, from this point on, you can also still flip the fraction because, again, really any lone number by itself, you can kind of just make it divided by 1. Because anything divided by 1 is itself. So it doesn't really make much of a difference for me if I put a 1 there. And now we can just flip the fraction again because we just made that into a fraction. And so now we have 1 divided by 0.1. And well, now we get the same answer. All right? The same answer. And then the alternative method I tell you on the Google Slides. Let's do 6b. Determine the total current running through the entire circuit. Right, so now my total current is question mark. I want my total current. And we solved in the last problem, my Req is 10 ohms. Right? And we know that my voltage is 6 volts over here. Now again, if I'm solving for my total current, when I use Ohm's law here, we'll have to use my total resistance as well. Okay, so we know my total resistance, my voltage is 60, IT is IT, and here I get 10 IT is equal to 60 divided by 10, and I get 6 amperes. And that's my answer. Now, 6C wants you calculate the area at which, calculate the rate at which battery supplies energy. The rate at which something supplies energy, that's power. And again, when you ever see the word rate, they really want to measure something over time. And they want to measure energy over time. And then energy, electrical energy, we know that's work. And so, well, what's work over time? That's power. So I want to know what power is. I want to know what the power I expend is. If you kind of take a look at the reference table, you kind of think back to 8.4. If you kind of look at the formulas for power, you see this. So they want the power for the entire circuit. So we want the total power. We want the total power. And if they want the total power, well, you can kind of use pretty much any one of those formulas, right? Because their total power is equal to my total voltage is equal times my total current. And we definitely know both of those. We know my total voltage supplied by the battery is 60 volts. We know the current, the total current running through this battery, or rather this entire circuit. We solved it, right? It was 6 amps, or at least I think it was 6 amps. It might not be. And now, well, if we do 60 times 6, what we get is 360 watts. But let's say you didn't know that power was measured in watts. Well, you're doing V times I, so alternatively, you could have given me the unit V times A. Right, and I would still accept that as the correct answer. That would still be the correct unit. Right, because all you're doing is just the symbols multiplied by itself. Now 60 says, if another resistor were added in parallel to the original circuit, what effect would this have on the current for resistor 1? Now, again, as we add more paths, because that's what's happening here, right? So another resistor is being added to this path. And let's see, 4 amps. The current running for resistor 1 was 4 amps, I think. And the current running for resistor 2 was 2 amps. Right? So my total current before the path was added, before this third resistor was added, was 6 amperes. Now, but what if we add a different resistor, right? So if we add another resistor, another path, we increase our current because we're adding more paths for electrons to flow. And so let's say we add this third resistor, and let's say the third current here is 3 amperes. And so now my total current here is no longer 6, but it's now 9. And so my total current would increase, right? My total current would increase, but would the current through resistor 1 change? Well, resistor 1, if we kind of use Ohm's law, we get resistor 1 is equal to V over I1. Unless the resistance of the first resistor changes, nothing else about this problem changes, right? I mean, rather, if the resistance of the resistor 1 doesn't change, well, then the current through resistor 1 also doesn't change. Your total current might change, right? Because you have an increase in current because due to adding another path, but your individual current does not change. So it does not change, no effect. No effect. No effect. So 6E, a 12-volt battery, causes 6 ampere flow, lamp is operating 6 watts. Draw on your reference, draw a diagram of your circuit. So let's draw a diagram of my circuit. So again, if you kind of look at the circuit symbols, right? So let's start off with battery. How do I draw a battery? A battery is 4 lines, right? So draw my battery, causes 6 ampere current. The flow for a circuit that contains a lamp. Well, how do I draw a lamp? And this is connected in parallel. So how do I draw a lamp? It's a circle with filaments. So that's the squiggly lines. And then the other one, there's a resistor. So that. And so that's R1, right? That's R1 and that's R2. And then that's 12 volts right there. And that's really my diagram. That's how I would draw a parallel circuit. 6F. Calculate the current through the lamp. So we know in the previous problem, my voltage was 12 volts. My current for the entire circuit is 0.6 amperes. The lamp, so that's power 1, that's operating at 6.0 watts. And the question wants me to find out, well, what is the current for the lamp? So what is I1? We know on your reference table that if you kind of look at the power formulas, you kind of have this is the only power formula that kind of fits, right? Because you only have V and I. So I have 6 here, I plug it in, 12 I1 divided by 12, 0.5 amperes is equal to I1. Okay? And that's my current through lamp, current through the lamp. And now I want to calculate, well, what is the resistance of the resistor? Now, you're looking for this, the resistor is R2, right? Because when we drew our circuit, we kind of labeled the lamp R1, and we labeled the resistor R2. So here we're looking for the resistance of R2. Now we know in the previous problem, what do we have? Well, we said that the current through the first lamp was 0.5 amperes. The total current was running for the circuit was 0.6 amperes. My total voltage was 12 volts. And my power was 6 watts. Well, power for the lamp, so P1. So I want R2, right? And really to solve for R2, I need to use Ohm's law. But unfortunately, when I'm using Ohm's law, if I'm solving for R2, I need I2. V is fine because voltage is the same across all resistors, so it's just going to be 12. But I need to know what I2 is. Well, thankfully, we know that the total current in a circuit, in a parallel circuit, is equal to the sum of the individual resistors, the sum of the current running through the individual resistors. And so my current here is 0.6 amps is equal to 0.5 plus I2. And so, well, if I solve for my second current, I'm getting 0.1 amperes. And so now I can finally solve for R2 using Ohm's law. Now, 0.1 amps, right? So 120 ohms. So R2 is 120 ohms. Yeah. All right. So calculate the resistance of the 40-watt lamp. This is going to be your power. Let's say that's P1. Say P1 is 40 watts. And calculate the resistance. So calculate the resistance of the 40-watt lamp. So it was R1. We know my voltage provided by the battery. It's a 120 volt source. And really the only power formula that kind of fits all of this is a V squared over R1. That's the only formula. If you kind of take a look at the other formulas, they all don't fit. So 120 squared R1 R times R1 144 divided by 40, and I get 160 ohms. Okay, I mean not 160, 360 ohms. 360 ohms. Describe any change. What change, if any, would occur if the power dissipated by the 100-watt lamp if the 60-watt lamp were to burn out. So if this 60-watt lamp were to suddenly stop working, would anything happen to, if any, would happen to the 100-watt lamp? Now again, if you lower the amount of paths, right? If you lower the amount of paths for electrons to take, well, you kind of decrease the current, right? You have less electrons flowing through, which means you decrease your total current, right? So this is your total current throughout the entire circuit. But when you decrease your total current, you increase your equivalent resistance, right? The less paths you have, the lower the current, the higher the resistance, equivalent resistance. But power, right? Power is really just dependent, if you kind of think about it, it's kind of V over V times I. But this, you care about the power by the third lamp, P3. And so the power done by the third lamp would equal to your voltage times your current running through the third lamp. But yes, my total current throughout the circuit might decrease, right? So my I total might change, right? My I total will probably go down, will most likely go down, but the individual current running through the resistor does not change unless the resistance of the resistor changes. Your total current changes, but your individual current does not change. And if your individual current, I3, does not change and my voltage does not change, then my power dissipated by this third lamp does not change either. So nothing would happen, right? Nothing would happen. Nothing would happen to the power. To the power dissipated by R3. Your total power would change, right? Your total power would definitely change, but your individual power would not change. That's something really important that you guys have to make sure you remember. The circuit is disassembled. The same three lamps are then connected in series with each other. Compare the equivalent resistance of the series circuit to the equivalent resistance of the parallel circuit. So in a series circuit, you have less paths, right? In a parallel circuit, you have more paths, right? The more paths you have, the more electric current you'll have, right? So higher current, higher total current, right? So higher IT, total current, and lower REQ because of that. Well, if you now connect it in series, you lower the paths, that means you lower the current, right? There's less paths for electrons to flow. And if you lower the current, you increase the equivalent resistance. Right? You lower the current and you increase the equivalent resistance. Now, which circuit has the smallest equivalent resistance, right? When you're looking for the smallest equivalent resistance, you're looking for REQ. Now, which gives you a smaller equivalent resistance, right? The less paths you have, the higher resistance, right? So if you want lowest equivalent resistance, the lowest total resistance, you want the most paths. You want more paths, right? So these two are wrong, right? Because there's only one path for these electrons. And B, there are two paths, but when you compare A and B, you'll see that A has 4 paths. A is a parallel circuit, so you're going to get the smallest resistance with the most paths. 6H is also another. So 6H says, well, you have two resistors, right? A 100 ohm resistor, a 25 ohm resistor. And you're trying to find out, well, determine the smallest equivalent resistance possible. Well, again, if you wanted to get the smallest equivalent resistance, you want to get, if you want the smallest equivalent resistance, you want to connect these resistors in parallel, right? The more paths you have, the less equivalent resistance you have. So they're looking for smallest equivalent resistance, which means I'm going to use my equivalent resistance formula in a parallel circuit to solve for this question. And so that's R1, right? So that's R1 and that's R2. So 1 over 100 ohms plus 1 over 25. Now, if we kind of look at the common denominator here, well, my common denominator is 100. Well, how do I get 25 to 100? We'll have to multiply it by 4. Right? So 25 times 100 gives me 25 times 4 gives me 100. 1 times 4 gives me 4. So here I get 5 divided by 100. I'm going to flip my fraction now. And I'm going to get REQ is equal to 100 divided by 5. And that gets me 20 ohms. And again, the alternative method here is to just do the math. Just solve for the fraction itself. So 1 over 100. 1 over 100 plus 4 divided by 100 gets me 0.05. And again, you can kind of just imagine that there's a 1 underneath it because anything divided by 1 is itself. And so let's flip it. So you have REQ is equal to 1 over 0.05. And now I have, what's 1 divided by that? I get 20. 20 ohms. And that's going to be my answer. Oh man, okay, it's over. I was running out of steam. Okay, well, that's it. That's this video.